Hello, welcome to Chapter 2, starting in Lesson 1. We're going to talk about segments overall, but specifically we're going to start with the real number subsets. And though the number line does come into the second part of this lesson, we're going to really just focus on the real number system and their subsets only. So the lesson essential question, how do we find the measure between points on the number line, will come in that second part of it whenever we get there. Just going to focus on the real number system today. Okay, hopefully all of these vocab words look familiar and that you're ready with your paper notes there to be copying this down. Obviously, if you need to pause the video at any point to catch up with the text, please do so. The first one is natural numbers. Natural numbers are counting numbers, so when you think about the numbers that you learned whenever you were a baby, you started with the number 1, and then 2, and then went on from there, so when you were learning to count, those are called the counting numbers, the natural numbers. Next, we have whole numbers. The whole numbers are natural numbers and 0. So now we're starting with 0, 1, 2, 3, and so on. Integers are the most common, but these are also the ones that we often call whole numbers accidentally or without thought to it. These are our positive and negative whole numbers. So we're now starting at negative, really kind of negative infinity, but only with those whole numbers, including 0, and now also the positives going on forever, again, just in those positive and negative whole numbers. Rational numbers are considered a ratio of 2 integers, any repeating or terminating decimal also. And this is a good time to notice that the natural numbers are the smallest here. It's just the shortest definition is counting numbers. But now if you look at whole numbers, the whole number definition includes natural numbers. Okay? And then the integers are positive and negative whole numbers. Well, there's the whole numbers, which are the natural numbers, and then the rationals are the ratio of 2 integers. So integers, whole numbers, natural numbers, they're all connected. The decimal part here mentioned with rational numbers is simply because any repeating or terminating decimal can be written as a ratio of 2 integers. Now, a ratio of 2 integers is just a fancy way of saying fraction. So when we talk about our rational numbers, we are talking about our fractions. The final subset are the irrational numbers. They are any non-repeating and non-terminating decimal, and also any non-perfect root. The concept of this bolded "and" here is because it has to not be repeating and not ending. Because if it's not ending, it means it's going on and on forever, but technically repeating decimals also go on and on forever. So it cannot end, but it is not allowed to repeat. Those sorts of decimals are any sort of non-perfect root. When we're talking about all of these vocab words, we really started from the most specific or the simplest and got a little bit more complicated, but all of these are subsets. All of these are subsets of the real number. So it's a set of all, not off, the set of all rational and irrational numbers. We will get a chance in a later worksheet to really see how these all fit together. But for now, one more additional piece of all these vocabs and these terms and these different subsets of the real numbers is how they can all be written. As many of us may remember, mathematicians are efficient. If we can shorten things down, then we will. So instead of writing natural numbers all the time, mathematicians now use just the letter N to represent natural numbers. W represents whole numbers. Z represents integers, which may seem funny, but it's actually based off of a different language where the Z comes from. Q are for rationals, I is for irrationals, and the R is for real numbers. Oftentimes you will see these more bolded, where it's more like the letter N, like this, where it's kind of got that bolded side to it. The W is more bolded on that side. The Z in the middle is bolded, maybe even the slash through it. So it's just this like font. I think I've even used it on a couple of the presentations, maybe even the beginning with the chapter. But that sort of bolded font is how you're going to see those letters getting written. So if you ever get tired of writing these words over and over again, natural numbers and whole numbers, you can start to use these letters also. Okay, so what you're going to want to do now is grab this Venn diagram that has been given to you with the real number system. What I want you to do is I want you to go back to the previous slides and previous moments in the video there and write down the definition of each of these subsets. Notice how the natural numbers are inside, then the whole numbers. Put the definitions inside each of their bubbles that they belong over here. This whole box represents the real number system, and then we'll go through and get some numbers and place them in there also. So pause the video and take a minute to write down those definitions and put them in the appropriate bubble, please. So hopefully your Venn diagram looks a little something like this with the definitions where they belong. I'll take this quick second here to discuss again just how this circle of natural numbers is inside the whole numbers, because all of the natural numbers included in the whole numbers. All of the whole numbers and natural numbers are included inside integers, and all of those are inside of rationals. There are some numbers that are out just living in the little section of the bubble here, but once it's in this bubble, it's automatically in this one and this one. And irrational numbers just kind of live off there on their own, because there are so many, or very few, that are considered irrational, and just specific types of numbers are in there, and they don't have any relationship with any of the other ones. So let's take a look at placing some of these. Okay, so -6 would belong as an integer because it is a negative whole number. 2.73 is a rational number because it is a terminating decimal. 3/7 is also a rational number because it is a ratio of two integers. The square root of 2 is irrational because it is a non-perfect square. The square root of 9, however, is actually the value of 3. So the square root of 9 is 3. So that is actually a counting number. So I'm going to put this weird square root of 9 here. But please understand that since I'm putting it in this natural number bubble, it is also a whole number. So the square root of 9 is natural and whole and an integer. And the same thing here. This -6 is an integer, but it is also a rational number. Okay? So -100 would be an integer, which is also a rational number. 0 is the only number. 0 is very interesting because it's the only number that lives in this section of this bubble here, because the whole number definition is natural numbers and 0. So 0 is the only number that's not a natural number, but is whole. Pi, this symbol next to the 0 there, is also an irrational number, so I'm going to put pi out there. 1 is, let's see, put that as a whole number. Well, we'll put it as a natural number because then it's automatically a whole number too. So the number 1, like I almost put it in the whole. Yes, 1 is a whole number, but only because it's technically a natural number. -1/2 is a rational. I know it may seem weird that I'm putting a negative number in the rational, but it is a fraction, so that's really what's putting it there. Same thing with -3.8, also a rational number. 5.42, since the 42 is repeating, that puts it as a rational number. And when you see something like this last number down there with the ... that means that it's going to be continuing in this same fashion as it already is. It does not mean it's going to be repeating. If I don't see a repeating pattern, then it's going to continue without a repeating pattern. If there is a repeating pattern there, then that repeating pattern will continue. In this case, this number 8.293,017 does not have a pattern, so it will continue without a pattern, making it irrational. So please include that in the irrational bubble. Okay, all in all, this Venn diagram is used to classify numbers within the real number system. So you notice this definition up here. It's the set, again, of all rational and irrational numbers. That's what a real number is. Any number that you can think of fits somewhere in this Venn diagram. Okay, when you go to classify a number, you want to look for the most specific one. Like the square root of 9, I said is 3. Yes, it is 3. And a 3 is a natural number, which makes it a whole number and an integer and a rational number, and therefore a real number. It's not irrational, but it is all those other things. The most specific, most correct answer would be a natural number for the number 3. So the only time that I would want to list all of those is if the question asks me to list all of the subsets that the number 3 belongs to. Otherwise, if it's just asking me to classify, the correct answer for the value of 3 would be that it is a natural number. Okay, so this chart is going to examine that a little bit further here. The number -7, we're going to just go down the chart here, which really is those bubbles from smallest to largest. Okay, well, and then the irrational numbers are its own bubble to begin with. So the number -7 is not a natural counting number. You do not learn to count -7 when you are a baby. It is not the 0 or all these natural numbers. The first column that I can put -7 in is an integer, which means it's automatically a rational number, which means I skip irrational and just go straight to real. The number 3/4 is a fraction, so that puts me straight at rational and real. Okay, so go ahead and see if you can finish off this chart. Go ahead and pause the video, finish off this chart in your notes here, and compare them in the next couple seconds. So here's that chart completely filled out. You'll notice that the number 5 has all of them completed. So if you were to have to put a mark for each of the subsets or to identify all of the subsets for which a number belongs, then you would list them all out. If you were just classifying the number 5, the number 5's answer would be natural number. The number 0.398 would be a rational number. Square root of 2 is irrational. 3/4 is rational. -7 is an integer. So we're going to the smallest bubble that they're in whenever we're actually giving it a name. All right, so the next thing you note is talking true or false. If false, explain why. So all integers are rational. This is true. And it's really true because if you remember that bubble diagram, all integers can be written as fractions. So I know it doesn't ask you to explain why if it's false, but I'm just going to go ahead and write that all integers can be written as rationals. So written as rationals are Q. So I'm just going to use those letters there. If a number is rational, then it must be a whole number. That's definitely false because a rational number focuses on those fractions, and it also can be negative. So it's false. So an example would be like -2/5. That's a rational number that is not a whole number, so it's definitely false. Number 3, some irrational numbers are integers. This is also false. An irrational number is off on its own, so there's no way that an irrational number can be an integer. So if I just give like the square root of 2, there's no way that that can be a positive or negative whole number. Number 4, all irrational numbers are real numbers. This is true. Okay, irrational numbers are just that separate bubble outside of the rationals. This is the big rational bubble. This is the irrational bubble, but they're all in the real numbers. Okay, all of them. So it's definitely true. No whole numbers are integers. That's going to be false because again, the way that we define these different types of numbers. If it is a whole number, like, I don't know, the number 5, it's automatically an integer by definition. An integer is a positive or negative whole number. So if it is a whole number, it's automatically an integer. All right, almost done here. As we take a look at rational versus irrational, I'm just going to use my letters here. Rational is Q, irrational is I. And so just some examples here. A rational number can be a negative whole number. It can be an integer. It can be a fraction. It can be a decimal that ends, so 0.05. It can be a decimal that repeats, so 0.05 with a repeating bar over it. Okay, but an irrational number is something like pi, or the square root of 5, okay, or the square root of 8. These are all numbers that are not perfect squares. There are a couple other letters, but even just a decimal that goes on forever. We saw something like this earlier, like that without a pattern. So notice, as I'm completing this chart, there's nothing in here. They have nothing in common. Okay, they have nothing in common. This is the Venn diagram proving that these have nothing in common. And if you look back at the diagram that we did with the real numbers, again, the irrational numbers were its own little bubble. The rationals were its set of relationship with bubbles, and they were all inside of real numbers. So yes, they are all real numbers, but they have nothing else in common. So I'll add that in there. Have nothing in common other than being real. Okay, being a part of that real number system.
All right, so this is the next part, kind of final part of your notes for this section with the real numbers, and I'm not going to give you any examples here. I just want you to kind of come up with your own. It just says write a number with 10 digits after the decimal point for each situation. So just read through those, just finish those out on your notes, and then we'll move on to some practice here. And I do believe that you're going to be using this video to help you complete a real number maze. So make sure you get that done and that you understand these notes are completed to help you with that number maze. Thank you.